Every branch of mathematics has a fundamental theorem. Fundamental theorem of algebra, fundamental theorem of statistics, fundamental theorem of calculus. Here is our fundamental theorem. Fundamental theorem of calculus is one of the focus here for standard 19. So FTOC, fundamental theorem of calculus for short, states that if f is a function that is continuous on the interval from a to b, and capital F is the notation for the antiderivative of f, then the definite integral from a to b of f of x dx is given by this expression. The antiderivative evaluated for b minus the antiderivative evaluated for a. Capital F of b minus capital F of a. What does this definite integral represent geometrically? You sketched this on your last quiz. If I draw the region given by this definite integral, what does it tell? The area under the curve, right? We used Riemann sums to find the exact area under the curve. Rather than using Riemann sums, I can take the antiderivative and plug in the upper bound, lower bound, subtract 2. It's a shortcut for finding the area under a curve rather than using some of those summation formulas on some notation. The definite integral represents the area under the curve, f of x, from a to b. Definite integral, the area curve. So this area is given by capital F of b minus capital F of k, where capital F is the antiderivative of function f of x. All right, so let's set up a definite integral to answer and evaluate this area question. Find the area under the curve given by function f of x equals x squared plus 2 on interval -2 to 2. What are the upper and lower bounds? From what to what along the x-axis by trying to find the area of them? 2 to 2. Or function x squared plus 2 dx. Here is the specific definite integral that matches the area given in the question. Now, fundamental theorem says we can evaluate that definite integral by finding the antiderivative and taking the difference when I plug in the upper bound and the lower. So let's first find the antiderivative, so I know what to plug -2 and 2 into. What's the antiderivative of x squared? I know it's going to be x to the, what needs to be out in front? If I take the derivative of x to the third, it's 3x squared. I want 1x squared. So let's multiply by 3 to turn it back into 1. 1. What's the antiderivative of 2x? I said the answer. What's the antiderivative of 2? I like to put a vertical line as the evaluation notation. So I know that I'm going to take 2 and -2 and substitute it into the function. I just kind of bring over those same upper and lower bounds here. And now my next step is to find capital F of b and capital F of a. Plug in b to the antiderivative. Plug in 2 to 1/3 x to the third plus 2x. Plug in -2 into 1/3 x to the third plus 2x, and evaluate by taking the difference. Plug in 2. One-third times 2 to the third plus 2 times 2. I have to put that in one single quantity, because what comes next is what I'm subtracting from that.
Report to the secondary office. Morgan Robinson, please report to the secondary office.
Your negatives can get tripped up quite easily because I have a subtraction sign in the middle. So watch your negatives, watch your signs. Minus f of a. Evaluate the antiderivative for our lower bound, -2, our a value, after I plug in the upper bound, our b value, positive. 1/3 times -2 cubed plus 2 times -2. It's 2 to the third. 8, so 1/3 of 8, or 8/3. 2 times 2 is 4. -2 to the third would be what? So -8 thirds. 3 -2's multiplied to make -8. -8 times 1/3 is -8 thirds. Add on -2 times 2, or -4. We need to find a common denominator to add up 8/3 and 4. So let's change 4 into terms of thirds. How many thirds are in 4? You multiply that by 3. So 12/3. Change the -4 into -12/3. 12 and 8/3 added together be 20/3. -8 and -12/3 added together is -20/3. Don't forget the minus sign in the middle. Once again, it's so easy to make a sign mistake. You have to bring down that extra negative. Minus -20/3. Final area, 20/3 minus -20/3 is really a double negative, so what is that? 40/3? (40/3) if I slide that down so you guys can see it there online. How we doing?
Good.
Good?
Good.
Good.
Outstanding. Fundamental theorem evaluates the area under a curve. Let me show you a couple of things on Desmos and the calculator. I'm going to share my screen really quick and put it up on the television here in the classroom. If you guys want to go ahead and get your laptops out or your calculators out, I'm going to show you how to do definite integrals using technology. Go to desmos.com and open up the grapher, not the calculator, the graphing calculator, not the scientific calculator, the graphing calculator. If you open up the keypad and go to the functions menu, under the miscellaneous tab is a definite integral. Or I think you can just type in INT for short. If you type in INT to the formula bar, it just automatically pulls up the definite integral. You can click definite integral. So we're going to do the definite integral from -2 to 2 of quantity x squared plus 2. Put that in a single quantity so Desmos knows what you need to take the antiderivative of. Don't forget the dx. If you want to turn that decimal approximation into a improper fraction, it's 40/3. On a graphing calculator, if I pull up my TI calculator, hi Justin. This pulls up. There we go. All right, so I have the equation x squared plus 2 graphed here. Should clear that out, actually. Type in x squared plus 2. So we know how to type that in. You can hit graph. And it graphs that region on your graph there too, right? To get the graphing calculator to evaluate the area under the curve, do you see where it says calc in like little yellow or blue letters above the trace key? That's the second option for the trace key. So let's go to the calculate menu by hitting second option, trace key. Option number 7 should be the definite integral option. So I'll select option number 7. And it says, all right, let's do a definite integral. But first, what's the lower limit? What's the lower limit? -2. What's the upper limit? 2. I like this one because it also gives you a visual representation of the area you're finding. It graphs the area for you that Desmos didn't. I wish Desmos, when you did a definite integral here, would actually graph that region on the picture, on the graphing field, but it doesn't. I've written to Desmos. I've begged them, please, please, show the area when you're evaluating a definite integral. They haven't gotten back to me. Texas Instruments, fortunately, did that for you already. I got about 13.33 down below, which was the same 40/3 we found on Desmos. There's also a different version. If you don't want to use the grapher, there's a different way to evaluate a definite integral on your calculator. If you go to the math menu, by selecting the math key, option number 9 is the integration of a function option. Select option number 9, and we can type in the same thing as on Desmos, -2 to +2 in the upper bound of function x squared plus 2 dx. About 13.3 repeating. I can let the calculator change that to an improper fraction by going back to the math menu and convert to a fraction with option number 1. Change the answer into a fraction, please. It's 40/3. 13 1/3 or 40/3. One nice way to use technology to check your work. Try a couple more definite intervals, just to get some good practice. Do a trig example. We're going to evaluate and find the area under the function cosine x between 0 and pi/3. Fundamental theorem says I need to plug in pi/3 and 0 into the antiderivative and then take the difference between them. So what is the antiderivative of cosine? The derivative of sine is cosine, so the antiderivative of cosine better be sine. Plug in 0, plug in pi/3. So sine of pi/3 minus the sine of 0. It's the sine of pi/3. What is an exact answer in terms of either root 3/2, root 2/2, 1/2? What are those different numbers on the unit circle you could look up? It's a special right triangle. Sine's opposite to hypotenuse. Is it root 3 over 2?
Yeah.
It's the sine of 0. Let's do another radical one. It's the definite integral, evaluated from 1 to 8, of function root 2 over x. Just like the one on your quiz that we practiced earlier, a little more clarity on. I got to do some rewriting. I can't just take the antiderivative the way it sits right now. How can I rewrite the square root of 2 over x? Take the square root of a fraction. You can take the square root of both the top and bottom. That's one way to think of it. How else can I rewrite it to get to a more easily antidifferentiable version? So I'm going to rewrite a radical as a 1/2 exponent, and then make it negative to bring it up from the bottom. Sounds reasonable. Let's call this the antiderivative, the definite integral, from 1 to 8 of the square root of 2 x to the negative 1/2. What's the antiderivative of x to the negative 1/2? We've got a better form to take the antiderivative of now, so let's do it. What's the antiderivative of x to the negative 1/2? Add 1 to the exponent. 1/2. When I take the derivative of this, it's 1/2 x to the negative 1/2. I want it to be equal to the square root of 2. 1/2 times what makes root 2? Trying to put something out in front. So I get the square root of 2 when I take the derivative. Right now the derivative is 1/2 x to the negative 1/2. I want it to be the square root of 2 x to the negative 1/2. Half of what makes root 2? The square root of 2. X to the 1/2 is the square root of x. So this is really 2 root 2 times the square root of x, which is the same thing as 2 root 2x from 1 to 8. Let's plug them in. 2 times the square root of 2 times 8 minus 2 times the square root of 2 times 1. What's the first term? 2 times root 2 times 8. 8. 2 times 8 is 16. Square root of 16 makes 4. And the 2 on the front times the 4 here makes 8. Very good. I don't think the next one quite simplifies as well, because 2 times 1 isn't a perfect square like 2 times 8 was. So let's just call this 2 root 2, minus 2 times 2 radical 2.